Hey everyone, today I'm here to show you how you can do electron configurations without needing to carry around an off-bow diagram all the time. Instead, you're going to be just relying on a periodic table. You might not see it yet or realize it, but the periodic table actually is a kind of off-bow diagram and can be used as such to write electron configurations. So you won't have to use these anymore. Let's get rid of them and get going. Now, up until this point, what you've been needing to use to write an electron configuration has been an off-bow diagram. And so, for example, for an element like manganese, when it's neutral, it has 25 electrons. And you know that because its atomic number is 25, so it has 25 protons, and to be neutral, it needs 25 electrons. Now, to place those 25 electrons, what we've been doing is using an off-bow diagram and putting the electrons in the lowest energy level first and working our way up. And then using this to write the electron configuration: 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d5. Now, it's terribly inconvenient to always have to rely on this diagram, but one thing that we notice about this diagram is that at every s sublevel, there can be 2 electrons, whether it's 1s, 2s, 3s. At every p sublevel, there can be a total of 6 electrons always, because there are 3 p orbitals each that can hold 2. At every d sublevel, there can be 10 electrons total. And at every f sublevel, there can be 14 electrons total. And what's interesting is that the periodic table is actually arranged to reflect this. Just like how each sublevel can have 2 electrons at most, this block of the periodic table is 2 elements wide. Because this block is 2 elements wide, it is called the S block. We also, to look at this pattern, assume that helium would be moved here from its current location. This part of the periodic table is 6 elements wide, and it is referred to as the P block. This part of the periodic table that is 10 elements wide is referred to as D block. And this part of the periodic table that is inserted here, lanthanum and actinium should go here and here, in which case, starting with cerium and thorium, we would have 14 elements wide, and this is called the F block. And the reason that this is going to end up being like a substitute for an off-bow diagram is that, let's say for our manganese, we can start at the beginning at hydrogen and think of each of these blocks as being electrons that get placed into a certain sublevel. We would say that this, because it's the first row, is 1s, and we would move 2 elements over. After that, we would move to the 2s, and we would move 2 over. And so we have 1s2, 2s2. We next would be moving to the 2p part of the periodic table, and we would be moving over 6 places. We would now move to 3s, and we would move over 2 places before we move to the 3p section, and we would be moving over 6 places until we move to the 4s part of the periodic table, where we would move 2 places. And now, because the off-bow diagram has 4s but then 3d, the D's are offset by 1. And so while this is 4s, here is 3D. This would be the 4D row, 5D, 6D. And so we would say 3D and how many spaces we move over. And so we can see that because manganese is the 5th element in the 3D section of the periodic table, it's going to end with 3D5. For F block elements, starting at cerium, the D block was shifted down 1, and so it started with 3, but the F block is shifted down 2, and so this is 4F and 5F. We can see how this works with another example. We'll do molybdenum, and we'll do the noble gas configuration, which means that we would start with the noble gas that comes before it, krypton. And from krypton, we would then be into the 5s, and we would move over 2 places. We would be into the 4D section, and we'd be moving 4 places. What you can also notice now, if you do enough of these, or if you look at a periodic table that has the electron configurations, is that all of these elements in this column end in S1, meaning that no matter if it's 1s1, 2s1, 3s1, 4s1, 5, 6, or 7s1, they all end in S1, meaning that they have one S electron that they can lose easily. All of these end in S2. All of these would end in D1, D2, etc. All of these end in P1, P2, and P6, excluding helium, which according to this pattern should be here. And so you can now see that instead of needing to carry around an off-bow diagram, as long as you remember that the D block is shifted down 1 and that the F block is shifted down 2, so the D block starts at 3D and the F block starts at 4F, you can do electron configurations without needing to use an off-bow diagram anymore. So I hope that all made sense, and now you can write electron configurations very easily compared to before, and you don't need to use your off-bow diagram and draw all of those arrows. You can just see where an element is placed on the periodic table. It also will help you next week when we talk about patterns on the periodic table and understanding patterns of reactivity and how they relate to an element's electron configuration.